Okay, I think I'm going to start. Hello, everybody. My name is Jürgen Gerhard. I'm Senior Director of Research in Maplesoft. I've been with Maplesoft for 23 years now. And I'm uh, happy to show you a few of the new features in Maple 2025, which you may have missed. So you will see a list of all the new features, but since I only have half an hour, I will focus on the real gems, and you can look at the other ones at your leisure if you have a copy of Maple 2025. Regarding questions, so I actually like it if you don't wait with your questions to the very end, but feel free to post them in the chat during my talk. And my assistant Jeremy will interrupt me if there is a question that I should answer. Okay, I will start with the user interface. The biggest new thing in Maple 2025 is that we have a new user interface. We have a ribbon now, like many other software tools. So things are a little bit better organized than they used to be. I'll leave it to you to discover yourself. Some of the things have moved to different places, so maybe a little bit hard to find at the beginning, but you'll get used to it. Another user interface feature that I would like to highlight here is scrollable matrices. We've had scrollable matrices in Maple for a few releases, or for one release at least, I think. What's new now? So what does scrollable matrices mean? So if the matrix doesn't fit on your screen, there's a scroll bar where you can scroll up and down to the section that you want to see. What is new now is that there is the ability to resize this. So if you get here, then you can drag and drop it directly, drag it to whatever size you would like. Okay, I will move on to an area that's very close to my heart, the mathematical core of Maple. There's many new features in here, which I've listed here, and I will be able to present only two of those, the partially ordered sets package and a solver for complex functions. A partially ordered set is just a set equipped with a relation that's reflexive, antisymmetric, and transitive. And it's usually denoted by this symbol here. And I'll give you one example. That's the partially ordered set is typically abbreviated as POSET, which is easier to pronounce. And the package handles only finite such sets, not infinite ones. Okay, and what do we take as our set? We take the divisors of 2025. So that's a finite set. And we define the divisibility relation on that set. And then we can construct our partially ordered set using the partially ordered set constructor. There's a drawing command that displays this. So you can draw this. This is would be the Hasse diagram of this partially ordered set, which only draws the minimal sets of arrows that are necessary. For example, if you have, but since it's a transitive relation, since 27 divides 135 and 135 divides 405, we know that 25 also divides 405, but this arrow is not drawn because otherwise you would see too many arrows. Okay, so then there's a number of properties that such a POSET can have. It can be graded, it can be ranked. We can ask what the rank is. It can be a lattice, that's true. It can be a face lattice. It has a width and it has a height. Both of these are very obvious from the drawing, actually. Okay, I won't have time to go into the next example, but another nice example is the face lattice of a polyhedral set. Instead, I want to talk about a different gem, new feature. We now have a solver for complex functions, or specifically targeted towards complex functions, in particular ones involving the absolute value and the conjugate. And here is an example, and the command is called complex solve. And you get, this is something that has finitely many solutions. Okay, I can see that there was a question in the chat, but I couldn't see what it was.
Yeah, John Pays asks, can you relabel the nodes in the poset lattice?
The labels are just the elements of the set. So whatever elements of your set you pick, those will be the labels. You can also store the graph as a Maple data structure, and then you can manipulate the graph. In that graph, there's graph theory commands that allow you to relabel the vertices. Okay, I'll move on to my third section here, expression tools. So this is a really cool new feature. So I'm showing two expressions to you, E1 and E2. And visibly, I mean, if you have a very sharp eye, maybe you can tell the difference, but just by looking at them, you can't, right? And if you use Maple to ask, are these the same? Maple will tell you false. So we have now a new tool called expression tools, and that has basically one command, and that command is called compare. And what it does, it will syntactically compare those two expressions, and it will highlight the difference. So here, the difference is in the subscripts. So the D has a different subscript. The subscripts in the first expression are labeled in green, and the subscript in the second expression are labeled in pink. For simple expression, the markup is done in a slightly different way. You see, instead of seeing both expressions combined, you see them separate and with the differences highlighted right underneath each other. And you can also customize this. So here's a larger example where I can say, how do I want the difference? Do I want to see a highlight for a missing operand or not? In this case, we have suppressed that. And do I want to see brackets for the differences or not? Okay, there's a number of new features that are important for education, and I'm a bit biased here, so I'll start by one which I implemented myself, which is called radius of convergence. So let's say you have an infinite series and you want to know if it converges. So there's two new commands. One of the commands is called converges. So this is the harmonic series, and most of you know that it does not converge. Now I increase the exponent in the denominator and ask whether it converges, and the answer is true. So these are non-parametric examples. So here's a parametric example. It's a power series. The exponential series where the parameter is x. The exponential series is absolutely convergent everywhere. But here we take the power series of the logarithm. And now I can't say whether it converges or not because the answer depends on the value of the parameter. If I already know what the radius of convergence is, I can make the appropriate assumption, and Maple will tell me, yes, it converges for that. But I can also ask what is the convergent radius, and the answer will be 1, as we expect. And I have one non-trivial example for this power series here, where the coefficients are the middle binomial coefficients. And I'll let you think for a moment what the answer is. And then Maple will be able to compute it. Okay, the other thing I want to show, this is functionality we previously had already in the gfun package, but now there's a new top-level command which is able to guess what is the closed form for a particular sequence. So the first one is the odd numbers. The second one, I hope most of you recognize as the Fibonacci numbers, and you will know the definition of the Fibonacci numbers is the recurrence equation, but there is a closed form which involves the golden ratio, which you can see here. Here is one which you can probably readily recognize as an exponential sequence. There's a parameter start where I can say, okay, I want the sequence to start at 0 or at 1 or at 2. So this is a slight correction to make it easier. Here's another example, which is an exponential series multiplied by a constant. And here is another example of a linear sequence. Okay, on to education. Sorry, visualization, my mistake. So this is a small improvement here. So this is something we could already do in previous versions of Maple. You have a curve defined by two data sets, a set of points and a set of values, and then you want to plot that curve. What is new is that now you can plot units associated with those data sets as well. So let's say the x values are all in seconds and the y values are all in meters, then I can now directly give this to the plot command without having to do anything special. And you probably don't see it very well, but the units will be displayed on the axis here. So the meters is on the y-axis and the seconds is on the x-axis. Another new plot feature that I want to highlight is the sparse option for matrix plots. So I'm generating a random graph, and then I generate the weight matrix for that graph. And this is a sparse matrix, so it has many zeros because the weights correspond to the edges that are actually present in the graph. And if I plot this graph just like this, it looks like that. But if I now use the new sparse option, so that's, sorry, this is what it's called, then you will visually see that it's sparse. So here you have these many gray areas which correspond to the default coloring that's being used. But for the sparse option for entries that are identically zero or that are not actually present in the matrix, no square will be drawn at all. So it's much easier to see the structure here.
Can we interrupt you before you go on too far, Gerhard? Jürgen, sorry.
Yes.
There's another question from Gerald. He asked, what would the sequence command recognize a list of successive prime numbers?
So I'm doing something which I shouldn't do, namely try something which I haven't tried before. I can give you a guess what the answer is. Did I do? Okay, I made a typo. So that's not the answer we expected. So I would have guessed that the command can do it. And the reason is this command is targeted towards sequences that satisfy a recurrence equation. And the prime numbers don't satisfy a recurrence equation.
Can you delete one and try again? Okay.
Were there more questions or should I continue? Right, I'll continue. I think I'm done visualization. So my next topic is graph theory. Graph theory is always fun because there's lots of nice plots. Again, we have one developer who adds a number of new commands to the graph theory with every release, Stephen Forrest, if you know him, so that's great. So we have about 15 maybe new commands and improved commands, and there already is a substantial number of existing ones, so over 200, I would guess here. So it's a very nice package. Okay, and I picked a few gems here. So anybody know what or most of you can guess what a Platonic graph is. The graph theory package has a number of built-in special graphs, and of course it has commands that generate those Platonic solids, but that would be kind of cheating. So here I'm directly, manually, so to speak, generating a tetrahedron, regular tetrahedron, by specifying the edges, and that is being recognized as one of the 5 Platonic graphs. And then I'm giving another one which is a slight modification. So tetrahedron is a pyramid with a triangular base, and here I'm constructing a pyramid with a square as the base, and that is not a Platonic or the graph of a Platonic solid. So the answer is false. I did not know before preparing this demo what a caterpillar tree and a lobster tree is. So let's see an example. So a caterpillar tree is a tree for which there is some path and in the tree, so that every vertex is either on the path or a neighbor of the vertex on the path. So here you can guess that the path is 1, 4, 5, 6, 7, and then 8, for example, this one or that one. And all the other vertices that are not on the path, they're of distance at most 1 to that special path. Okay, so the answer is it's a caterpillar tree is true. And then there's something which is closely related. It's called a lobster tree. And that is basically one with distance 1 more. So if you remove all leaf vertices, then you get a caterpillar tree. So you can pick a path here that starts here and then maybe goes down here and here, but then these two are of distance 2 from that special path. But if you remove those 2, or even that one, which is also a leaf, or that one, then you end up with a caterpillar tree. And there's 2 new special graphs. One of them is called the F26A graph, and the easiest way to understand it is to plot it. It looks like this. And then there's the Hanoi graph. And the Hanoi graph is a graph that models all the valid moves in the Towers of Hanoi game. And this is a Tower of Hanoi game with 4 disks. And you can do it with a larger number of disks. And then, the number of moves become exponential overall. But you can see this, I believe this is the Sierpinski triangle. So this is if you increase the dimension here, you will get a fractal. Okay, there's a number of performance improvements in Maple, and I only want to highlight 2 of them. So the first one is not really a performance improvement. It's just a new command which has an excellent performance to compute the pop count. So the pop count is the number of 1s in the binary representation of an integer. So here's an example of an integer with, I think about 100 decimal, no, it's more than that. Yeah, 100 decimal digits and converted to binary, so it's about 200 something. And here I'm taking a much larger number. So instead of 100 in the exponent, I take 100,000. And so every other, so there's the ratio of 0s and 1s is 2 to 1. So the answer that you would expect here is 200,000, and that happens within a second. Here's a nice performance improvement for solving differential equations. So numerically, you can use the dsolve command. By default, the dsolve command gives you back a procedure that allows you to evaluate the solution to the differential equation at an arbitrary point. And that procedure can be parametric. So I gave it a differential equation where one of the initial values is a parameter and one of the coefficients in the DE is a parameter. And I can initialize those parameters to certain points, and then I can say, give me the columns in the array output. So that would be time, the function itself, its derivative, and the parameter values. And then I can say, okay, do the simulation, run this procedure for values between 10 and 101, and then I get an array back for that. And I can change the parameter values. So here I don't have to recompute the solution function. I can use the same solution function, so it's very quick, just for different parameter values, and get back a different array of solutions. Okay, I have 2 more chapters here, and then there's some more room for questions. Programming, this is a nice little feature. It's now possible to do an assignment to a vector. So I can have a vector of variables and a vector of values, and that does performs a simultaneous assignment. So X, Y, and Z now have those values 2, 5, and 3. And another improvement is this has been around in Maple for many releases. You want to sum over the elements of a vector, and you're using the sum command. And in previous versions of Maple, if you tried to do that, you would get an error. And the reason is the sum command is really made for symbolic summation, not for adding up all the elements of a data structure, but it's a very nice and very natural notation. So a lot of people use it, and they will be very annoyed if this just doesn't work. And now it actually does work, even though the add command is technically the right thing to do here. Yep, those were the things I wanted to show about programming, and I'll conclude with one connectivity feature. So we've already heard about Markdown in the previous session. Rob Corliss talked about Jupyter Notebooks, and apparently Markdown is a type of markup language which you can use in connection with Jupyter Notebooks. Now you can also use it in Maple. So there's an example Markdown file which we ship with Maple, and it looks like this. So it basically looks as much as possible like regular text, and then there's some markup characters like this for italics, and this for bold, this for headings. You can have links, you can have images, and so on. Okay, so this is just a text file. And we can import that file using the from Markdown command. And there's two ways how you can get the output. The first one is what I'm using. You can directly insert the output into the worksheet, and then you see what the formatted output would like in Maple. So the headings get translated into Maple headings. Italics and bold is pretty standard. Images get translated into images into the Maple worksheet, and links get translated into hyperlinks, which Maple supports, as you can see. And finally, there's also LaTeX formulas, which I forgot to point it out, which are available in Markdown, and they will be converted to actual Maple expressions. Okay, and I'll stop here and see if there's any more questions from the audience. Thank you very much for your attention.
There's a question from Selden that the online encyclopedia of integer sequences has a very large number of sequences. Is there any thought that this list might be included in Maple?
I believe we have there is an app somewhere, or an example document that shows how you can connect to. So the OEIS has an API, and you can connect to that API, and then you can use the results from that in Maple. So that's something that's not too hard to program yourself. We don't have it as a feature that ships with Maple, but I'm pretty sure it's somewhere in our example documents. I just would have to dig for it. But there's many other web services that one could connect to, and it's with a little bit of programming and HTML knowledge, you can implement that yourself. Yes, so I'm seeing your comment here, Selden. If Maple if in Maple I get a sequence, it would be very nice to able to know without leaving Maple whether the sequence is a known one. Yeah, so we directly do not have this functionality right now. Again, there is this app or this example document which Dave pointed out in the chat, which can do that for you. We have something similar functionality for groups. So for example, if you would you can define your own group either as a permutation group or as a finitely presented group. And if the group is small enough, there's a command in the group theory package in Maple. I'm not sure what it's called. Maybe it's called identify group, which can give you, which has a built-in database of all known, at least simple finite groups, and it can give you the, if you don't know what your group is or what it's isomorphic to, you can ask that question and you will get the answer back in a similar spirit as what you're asking about the OEIS. Okay. There don't seem to be any more questions. So thank you very much for attending.